A few years ago, I was having lunch with colleagues at the International Symposium on Market Architecture, and we were lamenting about the state of the benchmarks. It seemed like no one could get it right. People were benchmarking single applications, focusing too much on vision and ignoring accuracy, and there was a need to do something better. When I got back, I asked my team to look into building a new benchmark, and those were the early days of what eventually became MLPerf. This talk will cover what is MLPerf, what is the benchmark that we built for benchmarking machine learning performance, and what were the lessons that we learned along the way. We expect that these lessons will be useful to you in your work in building a new benchmark. So what is MLPerf? MLPerf is a machine learning benchmark suite with broad industry and academic support. You can see some of the list of organizations that have supported, helped develop, and have submitted to MLPerf. MLPerf has become an industry standard for AI chips. The leading companies in the world who build the fastest AI chips in the world submit to MLPerf. Everyone today is aware that computers are much faster than they were in the past. John Massey is a believer in statistics. His wife teaches statistics. He's talked extensively to computer architecture audiences and taught us the basics of statistics. In 1980, John was CTO of a new chip company, and they were confronted with this problem of making computers, keeping up with the relentless pace of improvement of the speed of computers. And at that time, there were metrics that allowed measuring the performance of computers, but everyone seemed to be getting it wrong, especially the press. Some popular benchmarks at the time were Drystone and Whetstone, which effectively measured the rate that computers could perform instructions. They could perform potentially a lot of instructions, but not do any useful work. Another popular type of benchmark were called the Livermore loops. These measured time to perform real computations, but they were tiny problems. They were effectively toy problems, not representative of realistic workloads that were run in industry. So in the early days of MLPerf, John told us the founding story of SPEC. He explained how at some point around 1980, he was in a bar in Campbell with friends from multiple competing companies, and he was lamenting about the state of benchmarks and how they really needed to do something better. And from those discussions and that realization that there were problems, they realized that they actually already knew how to build benchmarks, how to measure the performance of their computers. They needed to do that in order to build those computers. They knew that they needed to measure the real workloads that their customers were actually running on their computers. And when they compared notes across which tasks are being run, they found that with a small number of samples or with a few benchmarks, they could actually get pretty good coverage. And even if a particular workload wasn't exactly the same as the workload that was being run, that was included in the benchmark, they were usually able to find one that was close enough so that a customer, and especially the people who are building the computers, if they looked at performance on that benchmark task, they'd very clearly get an idea of what performance would be like on their customer's workload. And SPEC was created. And computers got much faster, as we're all aware of, but it took a long time. So over the next 40 years, we've seen about a 10,000 times improvement in the speed of CPUs, the speed of computers that are measured using the SPEC benchmark. So there's enormous progress. 10,000 times enabled personal computing, or it enabled many of the products that we benefit from today. But it took 40 years. And that metric SPEC has persisted for 40 years. So enormous progress is possible, but it takes a long time. It compounds over a long time, and eventually it can add up to something very significant that can create an entire field. It's important when building a benchmark to think long-term. There are many lessons buried in the founding of spec. One is that it's important to think long-term. But another one that we already saw was that industry already knows how to benchmark products. We learned this lesson again when we started working on MLPerf. Before the first meeting for MLPerf, the lead engineer for DeepBench at Baidu, which is Baidu's internal benchmark that we use to measure the performance of systems that were deployed in Baidu, Sharon Narang, came to me with a concern. The right metrics, the right benchmark for Baidu would be different than the right metrics or the right benchmarks for other parts of the industry, for other companies. The first meeting was a really strange environment. We met at Google. This was hosted by Peter Mattson. And we had multiple groups attending. So we had the TPU group from Google. We had the Stanford Dawn group and the Harvard Fathom group. We also had a University of Toronto group. And we were really worried that we just wouldn't be able to reach consensus. So it was actually a really weird meeting. It actually coincided with the announcement of the Turing Award and the reception of the Turing Award by David Patterson, who was at the meeting. And of course, what do you do if you win the Turing Award? You have cupcakes. So the meeting was hosted with Turing Award cupcakes. But we're really worried going into that meeting that each party would just care about different things, that we wouldn't be able to find consensus. We wouldn't be able to build a benchmark that was reflective of what made sense for different companies. And it was really surprising, actually, to me, that as we started comparing notes of what are the workloads that were important for Google, for Baidu, we looked at Facebook also, we looked at Microsoft also, there was an amazing amount of commonality there. Not everything was the same, but by and large, it was actually very straightforward to essentially take the benchmarks or take the ideas that were already used internally, that were already used for measuring the performance of computer systems in Baidu and in Google and in Microsoft and in Facebook, and stitching them together into a coherent whole. And it was actually quite surprising to me that looking back on MLPerf, what finally emerged as the tasks that were selected for MLPerf, they're not actually that different from the benchmarks that were already used internally. The only thing that the meeting did really was it was just a recognition of there was actually so much commonality across the metrics. So in a space where there are already mature products being deployed in production, NVIDIA had been deploying GPUs that were used extensively. Google had just built the TPU, a new AI chip. There are multiple internal efforts in other organizations to do similar things. And I think the realization that we had is that when you're in a situation like that, where a technology is already being deployed in production, then there already are clear ways of measuring progress. And it's straightforward to create an industry consensus in an area where there are already products that are successful and have widespread adoption. It's just a matter of actually talking to each other and stating that there is that consensus. But that wasn't enough. So there were multiple additional challenges that we faced along the way. So the next story I want to tell is about how we adopted agile benchmarking. And multiple people had this concern. Multiple, especially of the academic advisors, they made a comments that there are just so many new technologies being released in deep learning at the time. This is around 2017. I think it's still true today that we see thousands of papers coming out a week. And it's looking back, we're able to point at major shifts in the models that are being used and the technologies that are being used. So there's this really rapid pace of innovation. And there was a real concern that, with the field moving so quickly, that any benchmark would just be wrong. So any benchmark would be out of date in just a few years. And so it wouldn't be able to survive that test of time like spec did. We wouldn't be able to select the tasks that would survive, for the next 40 years. And that was a huge concern of the group. So to address this problem, Peter Mattson proposed this idea of agile benchmarking. This is the recognition that in software engineering, we have the same problem that in response to deployment concerns, technology changes, the technology just moves extremely rapidly. So all artifacts, especially software systems, do not survive and must be continuously updated. And so the agile framework, the agile methodology is a way of rapidly responding to feedback and changes and adapting a software system. And so there's a realization that Peter had, which I think was great, was that benchmarks are software artifacts, just like platforms, just like a file system, they're a software artifact. And so we can also apply the agile methodology to them. So we launched what we called version 0.5 of the benchmark, which was what we thought was, the artifacts we thought were right at the time. And then with rapid iteration, we improve on them based on feedback. So one thing that you might imagine that we could change would be the models themselves. Actually, those have been relatively stable. We have made some changes, but things like the accuracy targets, we've adopted best practices like recipes for optimization that reduce variance in optimization. We've also adopted the software infrastructure. So benchmarks, we're measuring the performance of computer programs, that are written in software. And as frameworks evolve, as libraries evolve, that software changes rapidly. And so we're able to, without actually changing the model or the task itself, adopt new software technologies, incorporate them into the benchmark. And so I think it's, only being about 3 years in to MLPerf, it is a little bit too early to say whether agile benchmarking is going to be enough to allow us to adapt to a much longer time horizon. But we've already seen some initial promising signs. I think one of the large tests or the big test for us in the future is going to be the transition from a model-centric approach to a data-centric approach. But we already think that with the tasks that are selected with agile benchmarking, we can make updates to the benchmark and accommodate both model-centric benchmarking and data-centric benchmarking. We did encounter more challenges. One was the choice of metrics. So in spec, we essentially run a program and we just measure the wall clock time. How much time does it take for the computer to perform that program? Spec is heavily influenced by the C language, which has strong guarantees of data consistency. So you can provide input to a program, you can provide the program in C, and the C specification can guarantee bitwise exact outputs. So we can guarantee that the benchmark programs will be finished when they produce the correct answer. And we can verify that every single bit in that answer matches a reference. So machine learning, due to parallelism, floating point differences, and software differences, and also differences in the underlying hardware primitives, the underlying hardware operations that are supported by AI chips, cannot make strong guarantees like this. And so even though that metric of time to exact solution made complete sense for spec, we needed something different for MLPerf. And the solution came from one of the MLPerf contributors, Cody Coleman, who helped found the DonBench initiative at Stanford, was forced to create a solution to this problem. So Cody is a PhD student, working in machine learning systems and trying to build new technologies that would move the needle for his thesis. He struggled with the problem of just not having a clear needle, so the field not actually defining metrics well before MLPerf. And so he set out to define a metric and then move it. And so Cody proposed this, in the process of creating DonBench, they invented this new metric that had not been used in computer systems before, which they call time to accuracy. So this was based on the insight that even though hardware may have different precision and may have different order of operations, and floating point may have may have some errors associated with order of operations, um, deep learning models can still be trained to convergence reliably. And this is kind of a surprising effect that even though we know that the optimization landscape of neural networks has a large number of minima, all of which are different, that depend on initialization and order of operations, um, that modern methods, uh, modern deep neural networks like ResNets, trained with optimization algorithms like Atom on data sets, even if you do things like randomize the order of inputs on data sets like ImageNet, can reliably converge to um, the same target accuracy. And so in order to create this time to accuracy metric, the Dawnbench team, Cody and the Dawnbench team, they experimented with multiple metrics, actually explored many innovative aspects of metrics. Some of them didn't make it. So some things in practice turned out to be very hard, like including the cost of the system, because it includes market forces. It's actually very hard to benchmark over time. Um, but uh, you know, uh, the time to accuracy metric stuck, and it solved a clear problem that we had, and it allowed us to move on from the time to exact solution metric that was used in spec, and now we adopt time to accuracy as the way that we measure the speed of computers for training deep neural networks, and that's the metric that we use in MLPerf. So the last hurdle that we faced when we're building MLPerf was getting consensus. I remember an email exchange we had in the very early days of MLPerf where we were inviting the usual suspects to the committee to discuss the creation of the benchmark. And it was really hard to get one of the most important players in the space at the table. So we sent multiple requests to the NVIDIA team to help define the MLPerf benchmark. And I remember one response from Jonah Albin, their VP of engineering. Um, his response was, we see that there are a lot of Google founders on this group. How do we know that this isn't a Google trick? And actually, I can completely relate to Jonah's perspective because when I was working at Baidu, I was talking to our VP also, and that was exactly his response. Was how do we know that this isn't a Google trick? And that was a huge challenge because at the time, NVIDIA probably was deploying the most deep learning training systems, and many of the system integrators and cloud providers were actually deploying on NVIDIA. It just would not be possible to have a metric be an industry standard without being able to evaluate NVIDIA chips with that benchmark. And by a Google trick, I think what they mean is that because a benchmark, may be heavily influenced or defined by a competitor, what's to stop that competitor from stacking the deck in a way that favors them? So it was hard to resolve that problem. And the way it got resolved is through what we eventually learned to call grudging consensus. So we invited the entire group, all of the members that we believe would submit to a single room that was booked in Stanford. I think this was in the Gates building, and I forget who did this. I think it was Kunle or somebody, but they somehow managed to grab an hour in an auditorium in the Gates room, the Gates building between classes. And we packed, the whole room filled with all of the potential submitters to MLPerf. And we convinced NVIDIA to come too, just to hear us out. So when we were building the initial strawman design for MLPerf, we learned one clear lesson from spec, and that was to have a single metric. So the thinking and the rationale for a single metric or a single number. So when you run the benchmark and produce a single number that would determine essentially how fast your computer is compared to a reference system. So the speed up of your computer compared to a reference system. And the spec benchmark, had chosen a single number. So there's a strong historical precedent for doing that. And there's also a strong rationale. There was this belief that if you allow essentially people who are not engineers, who do not really understand what the metric means to interpret the metric, then they'll get it wrong. So if you release the raw data, but you don't draw the conclusion, boil it down to a single number, then you'll find reporters who, or people, in the community who explain the results in some way that's confusing and, actually leads to misinterpretation of the results. So if you don't, basically the idea is if you don't spell out exactly what to do, then people will do it incorrectly. And there's a strong precedent for doing that. There's a particular way of computing averages that was well known in spec as being the right way of doing it, and there being a clear justification for why to do that. But people frequently would not do that because they were just weren't aware of the somewhat subtle reasons why it made sense to use that particular approach. So in the meeting that we convinced NVIDIA to join, we laid out the design, and we essentially asked the community for feedback. And this was a point actually where I think NVIDIA had taken a serious look at it. They had their internal teams take a serious look at it. And Jonah came to that meeting and said, essentially, we're fine with everything except for the single metric. So it turns out that while spec, had adopted a single metric, the gaming industry, which had heavily influenced the NVIDIA GPUs, had taken a different approach where they essentially had single metrics, but for each task. So you can kind of pick and choose the games that you wanted to look at, the performance on particular games that you wanted to look at, and look at them individually. Rather than combining them all together into kind of an overall score across all games. And this was a real huge sticking point because, NVIDIA really, I think, had good reasons actually to not want a single metric. But because there was a strong historical precedence, this almost came to a vote. This almost came to a, let's just do a poll of the audience, and I think NVIDIA was the holdout there. And so it almost came to a vote, and because, NVIDIA would have been outnumbered, they would have been outvoted. And we actually wouldn't have reached consensus. We probably, that probably would have been a bad outcome. So we almost missed a consensus. But at the end of the day, I think actually the argument that NVIDIA made was a really good argument that, that experience with gaming was more recent than the decision that was made for spec, and there were good reasons for it. And there was also, as we looked more into it, we found there are ways of addressing the concerns of, not having a single metric, but also allowing essentially individual computers to show off their performance, maybe on some tasks, maybe there would be a computer that could be optimized for recommendation, and that might have unique advantages compared to a computer that was optimized for vision. And as we look deeper into it, it seemed like there were also ways of mitigating the concerns with the misinterpretation of results. So even though we might not have a single metric, we could still provide a recipe for if you must report a single metric, there is a well-defined way of computing it, and to make that clear. So essentially to coach the press when they report results so that they wouldn't misinterpret it and would report it correctly. And so eventually we gave into that request by NVIDIA. And because that particular point was so contentious, we called that our first grudging consensus, that everyone was a little bit unhappy about it, but at the end of the day, we had all contributed something to it. And so, I think that mechanism of grudging consensus was the only way that we were able to include NVIDIA. And, looking back, because of grudging consensus, we were able to get broad industry support, not have any major player who doesn't submit and doesn't participate in MLPerf. And if we would have gone straight to a vote, or, we would have pushed for perfect consensus, we never would have gotten there. So to me, I think there's a lot that can be learned by the linguistics community from MLPerf. I actually think it's a great time to build a benchmark in this space. I think this is especially true because products are already being deployed in this space. Many NLP technologies are used for search, for translation. Most of the applications, the keyboards that I have, the speech interfaces that I communicate with, the autocomplete of my email, they all use NLP technology. So they're already mature, highly impactful products being released in this space. And I strongly suspect that industry, if you talk to those product teams, they already know how to build benchmarks for this space. So we know that moving the needle takes a long time. So I think it's also going to be important for benchmarks in this space to think long-term. Think long-term, not just about consistency of the benchmarks, but about the organization and the structure and the community that needs to maintain that for a long period of time. And the space will absolutely have to be agile. Just like MLPerf, NLP is in a rapidly evolving environment. And we'd expect changes in tasks and changes in technologies to move at a very rapid pace. And I strongly suspect that metrics are going to matter and require insight too. The notions of entropy from Shannon have lasted a long time. But blending technology requirements and product requirements is going to require real insight. I think this community has the right people to do it. And finally, I strongly believe that you'll need consensus, grudging or not, to move forward. I think there's an enormous difference between the entire community moving in one direction and it moving in scattered, in scattered ways all over the place. It'll be hard to convince many competing companies to work together, but as we've seen in Spec and MLPerf, it is possible to do. I think I'll close with a note I just remember from my friend Peter Mattson, who was highly influential in creation of MLPerf. A clear objective for a field creates an environment where everybody puts in a little and gets out a lot more. This is a repeatable recipe. This next section gives even more detail about MLPerf. It's important that MLPerf was not developed by a single person or a single organization. It is the work of many. These are some of the early founders who contributed to the early design of MLPerf. And since then, the benchmark and the standard have grown to an active community of over 1,000 members. Why did it make sense to build a new benchmark? We know that there's a large market opportunity. We expect the market for AI systems to be greater than $60 billion by 2025. And especially in the systems community, it's clear from prior work that what's measured gets improved. What gets measured gets improved. And we've seen that from historical precedents. We've seen it in the speed increases in CPUs, in personal computers, driven by the SPEC benchmark. And we've also seen this in the DARPA Grand Challenge model. This community has those examples in our mind. We think of the progress that can be made when the entire industry moves in a single direction, even across competitors. These are some questions that we needed to answer while building MLPerf. And one principle that was very helpful that allowed us to answer these questions is to focus on our customers. To answer these questions from the perspective of what would a customer who would be buying a machine learning system, what is that customer doing? What is representative of that customer? So the first question is the benchmark definition. What is a benchmark task? And as we looked into customers of machine learning systems, we asked what tasks were they running? And that led us to discovering this first distinction that the two major categories of tasks were training deep neural networks and deploying or running inference on previously trained deep neural networks. This led us to separate categories for training and inference. And the second question is benchmark selection. Out of all the tasks that are being run, some of them are quite different. Which ones should we select to carry in the benchmark? Because building benchmarks requires resources, we can't include everything. And this is one reason why it's important to have a community define a benchmark. Any individual may be biased by the workloads or the tasks that they care about, but may not represent the entire industry. So you'd like a benchmark task to be simultaneously important in the sense that there are a significant number of consumers or customers buying AI chips who would be using these tasks. And you'd also like them to be maximally differentiated. So having many, even if vision is a very important use case, having many vision tasks might leave other areas like NLP or recommendation uncovered. Next, we have to answer, what is our metric? We have to define our metric. What is performance? In this community, the precedent has been speed. We buy computers based on how fast they are, how fast they can perform computation. And this is related to other metrics like energy efficiency or cost. But it turns out that in this space, we couldn't just use speed directly because it's easier to, especially for training, to train machine learning systems to lower accuracy targets faster. It's just easier to train systems to lower accuracy targets. There's this trade-off between speed and accuracy. And so we actually needed to develop new metrics that capture this trade-off. Another key question is, how do we perform comparisons fairly? This was especially challenging in a new field where many types of computers that were being built to run machine learning systems were vastly different, and they had very different software stacks. And so it wasn't just a matter of running the same program on different computers. They had very large differences in the computers themselves and also the software that would run on them. And so one challenge in benchmarking is making fair comparisons. How do we know that if two systems using completely different software implementations, and also, for example, using different underlying hardware primitives like precision, how do we know that they're equivalent? If one is faster than the other, how do we know that that is a genuine advantage versus a difference in the model or difference in the program that is being evaluated? And finally, it's important to deep dive into specific issues with individual benchmarks. We saw new types of issues that we had never encountered before in this community in both the training and inference benchmarks. So issues like quantization, calibration, allowing retraining during inference were questions that the inference benchmark needed to address. And related to implementation equivalence for training, there was a hard question about how many changes could be made to a model for those models to actually be equivalent. Was it okay to vary hyperparameters? What aspects of the model itself could be varied while still claiming an equivalent implementation? So let's look at some of the tasks that were selected to be included in MLPerf. Recall that because MLPerf was a community benchmark, we went to our community members and asked many of them who were deploying machine learning solutions which tasks were being deployed and which tasks had the highest value to that community. And then from there, we were limited by carrying capacity. So it takes a lot of work to build these benchmarks. Many of them had substantial design problems or design complexity. And we came up with these benchmarks: a vision benchmark, a speech benchmark, a language benchmark, commerce or recommendation benchmark. And then and these first four categories covered systems that we could point to that were being deployed in production to very many users at the time that the benchmark was being created. So they covered what we called the leading edge, but not the bleeding edge. And we also included this last category of research to include methods that were not being deployed widely in production as far as we could tell at the time, but based on the opinions of experts, gurus within the community, there was strong belief that these areas had the potential to be important in the future. And so we also included these workloads that we consider to be bleeding edge. And the process of selecting these tasks would be going to production teams, asking what are they actually deploying to their users. And because many of these were proprietary and it was actually difficult to get production teams to talk about, especially across competitors, to talk about exactly what they were deploying, we would instead ask them to point to a system or a open research paper, for example, that would describe a method that that team believed would be representative, and if was included in the benchmark, would be useful to them. And you can see some examples. So in vision, the image classification, object detection tasks were clearly important and already well known. In speech, we looked into both speech to text and text to speech applications, which we had feedback that both were important. It turns out that text to speech, because it actually generates speech, is actually very hard to evaluate. So it doesn't have a very automatically defined accuracy metric. And that made it more challenging to build a benchmark in text to speech. So the speech to text benchmark was released first. In language, there are actually a diverse number of tasks. It was actually quite challenging to find a task that was representative of the entire space. Translation did seem like there was some consensus around it, although the number of deployments of translations was smaller than some other systems. This became a little clearer after the emergence of embedding technologies like Word2Vec and BERT especially, that we found and received feedback from our members that were being deployed widely. So language modeling technologies like Word2Vec and BERT were included in the benchmark. And finally, as we looked into recommendation systems, although these are deployed widely in production, they have a very large number of users and it's clear what the algorithms are. We found it very challenging to find data resources that we could include in an open benchmark that could be used for recommendation systems. And so we actually partnered with a data provider to provide a data set so that we could build an open benchmark that could be shared across the community for recommendation systems. And in research, the first benchmark, which has actually survived the longest, has been reinforcement learning in games based on the AlphaGo work. This one especially was actually quite easy to build a benchmark for. So because it's a self-contained environment, this one was actually feasible to build a benchmark for. So the complexity of actually building this benchmark, I think, greatly influenced its survival in the early days and also continues to be part of the suite today.
So now that you know a little bit more about what MLPerf is, the last thing I want to mention is how to support it into the future. It turns out that building the infrastructure, the reference implementations, conducting the competitions, presenting the results, analyzing and presenting the results, ensuring fairness and quality of the submissions is a lot of work, and it's real engineering work. So if we want a benchmark that can last for a long time, we need to make sure that it has the resources required to perform all this work for a long time. And so in order to do that, we created a nonprofit organization. It's called ML Commons, which is supported by our members, so supported by the organizations that submit to the benchmark and shape the benchmark. They also provide the resources required to support the benchmark,